about more later. So let's talk about concept selection and parameter evaluation real quick. So concept selection refers to how you're going to manipulate your game piece, or what do you want your subsystem to do. Like if I was talking about a 2018 game where we're placing cubes on the scale, concept selection would be, am I trying to shoot the cube onto the scale, or am I trying to lift the cube onto the scale using an elevator? And then parameter evaluation is talking about the specific criteria that is assigned to this kind of stuff. So like, what is the most efficient way to do this? What measurement should I use? And how fast do I want my intake to grab my cube? So what are the advantages of prototyping? So with prototyping, the design decisions will become clearer and easier to make. So last year, in 2018, we had a conflict between our team where we're looking at designing either a roller intake or using wheels. It was a good debate for the first 2 weeks. And then instead of arguing, what we decided to do is we built 2 prototypes. The one that worked better ended up being on our final robot, which was the wheeled intake. And prototyping also allows you to help you realize which part of the game is hard and easy. Does anyone remember what the 2017 end game was? Yeah.
You had to climb using the rope and hit the touch button.
Yeah, so at first that looked really hard, but because we made a prototype, we were able to figure out that it's not that bad. All you have to use a rope and a winch. And instead of focusing our time and dedicating a lot of time to making a good mechanism for that, we could spend more time on making gear grabber mechanisms or ball grabber mechanisms. And then the most important thing for me personally for prototyping is that the measurements that you need for prototyping are generated from their prototype. So what some teams do, like 971 and 254, they CAD their entire robot or they CAD their entire mechanism and then they start building it. But a problem with that is you're not accounting for the real life occurrences of what might happen between the wheel and the game object. The wheel might compress a bit more than you expected, but if you prototype, you're able to get those measurements, and all you need to do is accurately measure the distances between the holes that you made, and then you're not guessing on any of your geometries. They're all set in your CAD. Okay, so this is the basic timeline that you'd be following for prototyping. So first you start with selecting your concept, which is what we call concept selection, and then you set your specific design criteria, which we'll talk about what that is later. And then you'll start building your prototype, and then you'll start recording and testing your prototype, and we'll talk about how you should test your prototype to avoid human influences, and then you're going to evaluate your prototype and see, is there a way that I can make it more efficient? And then you go back to your build cycle, and then you start doing that over and again. So prototyping for concept selection. So what that means is you're going to, on day 1, instead of starting away like, all right, I want my intake to be like this, wheels and everything, you want to start off with saying, this is what my robot's general strategy might be. So 2019, we started off day 1 with thinking, day 1 or week 1, we started off thinking that we wanted to have an arm that flipped across the robot that allowed us to reduce cycle time. So we have to design our intake mechanism around that. And basically what that told us is we want to have our intake mechanism for our hatches and balls in one mechanism so that it reduces weight and all sorts of complexity. And then this is where you want to set your general design criteria. So what is general design criteria? So you want to figure out what your subsystem is exactly doing. So what that means is if my subsystem is responsible for transporting the game piece across the field, your subsystem's goal might be to act as an intake. So that's one part of your subsystem that you want to figure out. And then you want to have quantifiable requirements for your prototype. So you want to say, oh, I want to intake my ball in all angles that I approach the ball at. That's a quantifiable requirement. At this stage, you don't need to have numeric requirements like, I want to intake my ball at 0.5 seconds. We're not at that stage yet. We're still at the very basic stage where we're trying to figure out how exactly we want this mechanism to function. And then one of the more important parts about generic design criteria is you want to avoid a language that suggests a particular design. So I'm going to refer to 2018 a lot, but if you're trying to say that if I want to score game cubes onto the scale, you want to say that instead of saying I I want to shoot game cubes onto the scale, or I want to lift game cubes onto the scale, because that limits your ideas just to an elevator or a shooter, and either one might have been beneficial if you thought about it in the first place. So brainstorming. So one concept to remember is no idea is a bad idea, and then the way that our team brainstorms during this build season or off season is that we look at past FRC and FTC games. So in 2018, what we did was we looked at the FTC game, which ended up being taking cubes and using an elevator and stacking them, and we're like, we think that the FRC and FTC game will be closely related. So for our off season, we built a mechanism that pulled cubes and a mechanism that lifted the cubes, and fortunately, that ended up being the 2018 game. You also want to look at unconventional ideas. I'll show you a few unconventional ideas in the next couple slides. And then one important thing is you want to try more than one prototype for your subsystem. You don't want to have just one prototype because that limits your ability to explore other options that are available for you. And the obvious idea might not be the best idea. So does anyone know what the 2014 game was? Okay, it's fine, but the 2014 game was aerial assist, and what it involved was using large yoga balls and shooting them into scoring areas above your driver station. The most obvious answer to everyone for scoring those was to use a pneumatic launcher, just take a large piston, put a plate on it, and just launch a ball. But some teams saw across that design and decided to use a shooter-based style. So what that was, they used large wheels of different sizes, and then they were able to shoot their ball into the scoring platform much more effectively, much more accurately. And I think 254, this team ended up winning that year's competition at Worlds. So you always want to give unconventional ideas to try. Since most of you didn't know what aerial assist was, I'll give you a more relatable example. So for 2019, can anyone tell me what were the main ways that people intake hatches? Yes?
Well, there was Velcro.
There was Velcro. Anyone else? Yeah?
Some sort of latch system on the outside or inside.
Okay, so I like how we all said all the ideas that I wasn't thinking. So this is an unconventional method. We looked at a bunch of wheel intakes after build season ended, and we're like, oh, this is a field that we should explore. So basically what it is that 4 of these mechanisms, and these 3 mechanisms revolve around the concept of intaking the hatch from the inside using wheels. You spin the wheels outward and then the hatch will move in because that's the circumference of the wheel, the diameter of the wheel is equal to the distance between this edge and that edge. So that's how those 3 mechanisms work. And then this mechanism simply works by intaking a hatch from the ground, and if you have a wedge on it, the hatch will move upward in the ground intake. And this was one of our prototypes that one of our lead mechs came up with last year, and what it was basically is you can see you outtake a hatch from either the bottom or top, and you can rotate this mechanism to pick up the hatch from the human player station or off the ground. We didn't use it because it didn't end up being that great. But does anyone remember what happens at the end of the game last year? What was the end game? Yeah?
Everyone kind of raced to climb onto the different platforms. There was just normal parking, then going, I don't remember the exact height, but there was one halfway point and then there was a highest point, which gave you the most points.
So the way that most people, that really good teams like 254 maximized their climbing points was that they used what was called a suction climb. So that's one of the other unconventional designs of 2019 in my opinion. Basically what it was is that they used physics and geometry to figure out at what angles and what lengths can they support the weight of their robot by using suction cup. You can also see, if you look at a top view, if you look at 1619's reveal video for this year, they show a really nice top view of how they take a fraction of the space while climbing up in this method. And I think 254 in one of their Einstein matches were able to get 3 robots using that kind of mechanism on level 3. So suction cup mechanisms are also quite effective. So the premise of these past 3 slides was to basically look at unconventional ideas. And you can find more unconventional ideas like these if you just go back to games that are similar to the current game. So in 2019, in taking a ball, we looked at 2014, since that was an aerial assistant that was intaking balls, 2016 that was intaking balls. But you have to remember that the games are not the same. So like the balls were different throughout the game. So in 2016, it was a foam core ball, so if you applied a lot of pressure to the ball would break. So that kind of mechanism would probably not be as effective for 2019 because the balls were a lot more structural and you could intake the balls a lot more faster and these were a lot more bouncier. Okay, so now we finished, at this point, we've just finished the first phase, which is selecting a concept. So at this point, you have multiple prototypes that your team wants to work on, and now we're going to focus on how to make each prototype a bit more effective. So that's called parameter evaluation. So earlier we set our general design criteria. Can anyone remind me of what an example of a general design criteria? Yeah?
Like intake from any angle.
You wanted to
It's like have an idea, right? Like this design.
Yeah. Basically. And then now in this phase, we're going to be setting our specific design criteria. So we want to come up with quantifiable performance goals. Like in 2016, a main focus of the game was to launch balls into a scoring platform that was quite high, like 10 feet high. And then you might want to say, I want my mechanism to score 80% of the time, or I want my mechanism to pick up a hatch panel in 0.5 seconds. And then the third one basically builds off, the third bullet point here basically builds off the second bullet point, and you want to have a bit more detailed aspects. So if you're designing a shooter, you want to test the different variables, such as how fast can you get your shooter to move so that it reaches its max shooting speed in the least amount of time. Those are the kind of things you want to be thinking about in specific design criteria. So knowing design variables. So what that is when you're building a prototype, you want to try to simulate true conditions when testing them. And what that means is, if you're testing a prototype with you holding it, you're probably not going to be moving the intake mechanism in the same method that a robot might move it. So one good way that we decided to avoid human influence is by taking a simple cart, adding a bunch of plywood blocks, and just mounting our intake mechanism onto there. So that's a good way to avoid human influence, since driving the cart while using the handles actually accounts for how the robot might move in the first couple of weeks. So another bullet point on this slide talks about a few more variables include rollers, wheels, material size, speed, etc. So by changing the difference between different wheels, green wheels and blue wheels, which have different parameters, you can get large impacts on how you intake the cube or how you output the cube, or if you change the RPM of your motors from 8,000 RPM to 5,000 RPM, you can see large differences. So it's always important to look at these design variables and manipulate them to your advantage. So here we see rollers versus wheels. And basically this just shows you two different ways that the 2018 GameCube was intake. A key benefit of the rollers was that you could intake the cube from a larger range of motion, and then the green wheels had a benefit since they're AnyMark compliant wheels, and they're really they're really flexible, and when you try to switch them, they'll bend to however you want them. And the way that they work is that if you move towards this side, if you move from red to blue to black, you'll eventually get more stiff wheels. So green wheels sold out really well in the 2018 GameCube because they were really effective. So here we see two more designs. Claw mechanism. This is a 254 prototype, and basically what they did is they built a claw mechanism to pull the gear from the ground, but unfortunately didn't use it in the end, since there was no way that they could move this gear into vertical position so that they could score it. And then we can see a classic example of a shooter bot from 2018. Okay, so now we're going to talk about how exactly should we build the mechanism. So when you're designing your prototype, you want to try to use as many FRC legal materials on your prototype. What I mean by that is, if you're using a motor, try to use FRC motors like Sims, bags, 775s. Don't try to use off-brand motors, since in the end it's much easier to account. If you start with FRC legal materials, it makes it easier for you in the end when you're putting it on your final robot. And you also want to implement as many adjustable components on your robot. An example of an adjustable component is surgical tubing to tension your mechanism. So if we go back right here, you can see that we have surgical tubing right here, and what that allows us to see are the best tensioning. If we just pull the surgical tubing a bit more, we can tension these arms a lot more. So little things like that are helpful in the first few stages of prototyping. And then you also want to try to manipulate robot movements, and the way that we use on our team to manipulate robot movements is using a robot cart, mounting our intake, or just slapping the mechanism on our practice robot. VersaFrame and 80/20 extrusion. So what VersaFrame is, it's stock metal, 1x1 metal that's sold by Vex, and it has 1-inch holes along a 1-inch line on all 4 sides. It's really easy to cut, so it already has holes in them. You can prototype mechanisms really easily. And 80/20 is also really helpful because it's metal bar with slots in them, so that you can slide intake arms to find your best center-to-center distance. And then sketching with CAD, which is you use simple sketches in CAD to prototype large mechanisms such as arms. Since if you build an arm in real life and it ends up being too short, your CAD could have saved you then, because CAD can show you a simple way to just draw a 2D sketch and you can tell if your arm is too small or arm is too large. We'll look at that in a couple of minutes. So here's a classic example of using Versa 80/20 in wood. So this is 1/48 2015 prototype. What they did is that they built their first prototype out of VersaFrame using materials that they normally don't use on their final robot. And then on the right we see Spartan Robotics building an intake for 2018 using 80/20 in wood. So you can see this wood and all that stuff is laser cut probably, but it doesn't have to be that complicated. You can simply use wood plates and it'll do the same job. As long as it works, it doesn't matter if it looks efficient, if it doesn't look as nice as theirs does during the prototyping stage. So here are what the end results were. So 1/48, since they always have to build in sheet metal, they decided to use sheet metal design for their final design. And then here is what 971 intake ended up being. One key difference we can see between the earlier design and this design is that 971's robot, their 971's intake was folded in earlier, now it's folded out. So you can see how prototyping generated you all of these measurements that you needed in the future. And here, this is what I was talking about with sketching with CAD. So this right joint represents an arm joint, a double jointed arm. So this is one point which an arm rotates, and this is another point at which an arm rotates. So what this is trying to simulate is stacking 3 cubes on a flat surface. So this arm shows me if this CAD shows me, is my arm long enough or is my arm too short, and it allows me to see if I have the right measurements or not. So you can, here's your ground, here are the 3 cubes, and here's the wheel that we're using, a 4-inch wheel, and here's the base of the robot. So adjustable components. So another type of adjustable component in FRC are versaplanetary gearboxes. Basically what you can do with them is they're a huge investment at first, but over the years they'll be beneficial if you're trying to, or down the line when you're like, say like a five-year team, and you can use them efficiently on your robot. During the earlier prototyping stages, you can simply just switch out a 5-to-1 stage for a 7-to-1 stage, or you can slap on more stages. That's why versaplanetary are one of our favorite things to use for prototyping. Sprocket and chain assemblies. So what I mean by that is you can use a chain assembly in which you have 2 holes, one hole for your motor and another hole for a pivot point. So in order to drive, say, a shooter wheel on your first shooter prototype, you can simply take a chain assembly here and then drill in a pivot point into the wood, and you can tension the chain by pulling the plate even further back or moving the plate towards it. And if you buy an adapter from a sim shaft to a 1/2-inch hex shaft, you can simply swap out sprockets and change the ratios really quickly. So that's why sprocket and chain assemblies can be useful during prototyping. So mimicking robot movement, that's another example of how you can mimic robot movements. So one of our prototypes for this year, all we did was like, okay, our prototype, we didn't have a practice drivetrain yet, so we put it on our 2018 robot to test it out and see if it worked. So that's also another way you can mimic robotic movements by just using older robots and older chassis. My bad. How do we power mechanisms on our robots? So there's two ways. There's motors and gearboxes. So motors and gearboxes will get you to multiple degrees of rotation and multiple degrees of movement, and then pneumatics will just get you from point A to point B. So pneumatics can be easy to repeat, but they don't have as much, how do I put it? They're not as good as motors since motors will almost always be your continuous type of intake. We'll talk about what continuous intakes are in the future, but key things to keep in mind with motors is if you're trying to get you're not going to always use your motor on a 1-to-1 reduction. There's probably no application FRC that has a 1-to-1 reduction, so you're probably using a planetary gearbox, reverse the planetary gearbox for reduction, or a single or dual shifter gearbox, depending on what the application is. One thing with planetary gearboxes I forgot to mention is don't use the 10-to-1 stages because they wear out very easily. If you have 9-to-1, 7-to-1, but just don't use the 10-to-1s. And with motors, you also want to make sure you have encoders on there so that you can measure how much the motor is rotating. And with pneumatics, you just have to wire up the pneumatic system. So, are there any rookie teams here that don't know what JVN is? Alright, so since you guys know what JVN is, we used JVN this year to get a basis of understanding of the numbers that we could use on our drivetrain. So we plugged in our drivetrain ratio numbers into here, and then it gives an estimate of how fast our robot will move. But I think in 2018, JVN told us that if we ran our elevator on a 10-to-1 reduction, that our elevator would go up in 0.8 seconds, which did not, and it did not end up working at all. The motors burned out, so we had to tone it down to a 20-to-1 reduction. So keep that in mind when you're using JVN. But it's always a good starting. It's always a good starting point for your resources during prototyping. Okay, so on the next slide, we're going to start case studies, and I'm going to ask you what the similarity is, and the similarity is not blue. What is the similarity between all of these robots? Not that either. It's not smoke Lexan either. What is it?
It was an active intake.
That's one of the similarities. We'll look at that later. What?
Massive.
No, we're not looking at. Look at the drivetrain of the robot.
West Coast.
Yeah. So, drivetrains. This is one of the mechanisms you don't want to spend time prototyping. You know it works. Usually, you'll never have to prototype a drivetrain because I think our teams use the same drivetrain and just change where the motor mounting locations are for the past 4 years. And West Coast, there's no problem with it. It's easy to build. It doesn't take that long to prototype. It doesn't take that long to assemble either. So just stick with West Coast or whatever drivetrain you're using for the next couple of years. So someone already said it earlier. So another similarity between all of these robots is that they're using an active intake. And what that is you're using rollers, intakes, and the mechanism is continuously moving. So it's what we call touch it, own it. Touch it, own it means it's those sort of intakes where it doesn't rely on driver skill as much, but if you're close enough to a game piece, your intake mechanism is good enough that it will be able to pick up that object really without relying on drivers. And then single intakes are usually either a claw or a hook. We looked at the 254 pull out intake earlier, that might classify as a single intake. It's usually powered by pneumatics. So here's a different, okay, so which one here is a continuous intake and which one's a pneumatic intake? Anyone? Stephen?
I think the, well, the rollers is a continuous, and then the one with the track, the blue thing on the inside is going to be stable.
Yeah, so that's a good 2018 intake, that a popular design that a lot of good teams copied, and then this was one of our designs, I think it was my freshman year that me and a couple of students built. We didn't end up using it since it wasn't as efficient as our other designs, but even though it didn't end up being a really good design, we used similar concepts like these throughout the robot during other years. And sometimes you might want to skip prototyping as well. So mechanisms like drivetrains, we don't have to prototype. And mechanisms like elevators and arms, they're so large that if you try to prototype them, you'll end up actually wasting more money and materials. So those are kind of things, let me rephrase, those are kind of things you want to CAD first, and then you might want to build two versions. One practice bot version and one race robot version, which is slightly different to be a bit more efficient. And anything that you can't, suppose like, I know we don't have a bag and tag this year, but if you don't finish a mechanism, you still want to leave something on your race robot just in case you don't end up finishing it. So, okay, now we finished the build phase and we're moving into what's known as the recording results phase. And what you do is you start testing your intake. A good way of testing your intake might be hooking it up on a robot cart and moving it around and see, can my intake pick up the hatches at all angles? Do I always have to be straight when I'm picking up the hatches? That might be one thing you might want to fix. And you want to make a lot of prototypes and make a lot of adjustments while you're doing this. And one important thing is you want to change only one variable at a time. So like if you see that your cargo intake's not picking up balls and you think, oh, the ratio might be too high and the wheels are not that good, you want to change only one variable at a time to make sure that you don't have to change it, to make sure that your other variables are fine. One way you should record this data is you can either record it on paper or you can record it on an Excel or Google Sheets. And
Wait. Listen.
Right here, I got it.
okay, we don't need to see that. So while testing and powering a prototype, you can see that this is one of our 2019 prototypes for cargo. And you can see when you're building a prototype, sometimes you don't want to have motors always. So skip the motor mounting stage and get drills and get hex attachments, or just put double-sided tape on it and just mount it to the shaft and start spinning it to simulate motors moving. And one other thing that our team does when we're testing and powering prototypes is that we made a compact pneumatic test board, and what that allows us to do, it's like this big. And instead of waiting for the practice robot drivetrain to be built, we just use this pneumatic test board to test our prototypes. We can see here we see a team called 971. This is how they tested their 2016 prototype, and basically what they did is that they're measuring the effect of changing wheel speeds, and the blue tape marks represent how far the ball went based on the changing the wheel speeds. Okay, now we've finished the recording phase. Now we want to evaluate. Is there a way that I can make my prototype more efficient? And you want to compare prototypes for the same subsystem at the same time. Be like, is there a better design that I can use? And this is where you can eliminate the designs that you don't want to use, and this allows you to not waste time while choosing between two ideas. Since you're basing all of your decisions off of pure hard facts instead of just, I feel that this is better. We're going to take a look at a couple of case studies of good prototypes and bad prototypes. So this is one of our 2018 freshman prototypes that I showed you earlier. And can anyone tell me what's wrong with this prototype? Yes.
Maybe Metal?
Yeah, that is the thing here. So, like, you can use metal, but I suggest using Versa frame metal since it's much lighter. It's not as premium as this 2x1 metal, and this prototype didn't end up being the best prototype. So we wasted a couple of materials by doing that, and so this is what we want to make sure we always use spare metal or Versa frame, or use 80/20 to be adjustable. So you can see here how we're testing our intake mechanism. So if you can see if you can spot the yellow drill there, that's what the slides meant by RC controller. We basically took out the drill mechanism in a drill, and then we just attached power wires so that the harder you press the trigger, the faster your motor spin. And you can see an early prototype of our winch for 2018. Keep in mind right now that winch assembly doesn't look as nice, and the chain is outside the tube, so that you can easily switch out your mechanism. So you can easily switch out your chain just in case something goes wrong. So here's more clips of our robot trying to practice. Can anyone tell me how many versions you think that mechanism's been on there until it got to the practice robot? Like 5 versions, 3 versions, how many do you think it was? 4. No, much higher.
10.
Higher.
Take it.
Lower.
20?
Close. It was 17 versions before we got it on there. So we've changed a lot of things. You can see we're using a bit more high quality pulleys. We're still using Versa frame because it ended up being good for us. So just because you used the material in prototyping phase, you don't have to switch to more premium materials. You can keep it like that. So this is what I meant by the difference in our winch. You can see it's a lot more compact. And winch is not really a mechanism that you can prototype since in our robot it had to fit in a confined space. But the major difference is that here that we were able to fit the chain in the tube and make things a lot more compact. Bless you. Okay, so Spartan Robotics. So if you guys don't know who Spartan Robotics are, they're a team that publishes blogs during build season of how far the robot's progress is. And unlike most FRC teams, they're actually open to I think they publish the CAD files as well, but they just let you know whatever they're doing during build season. So if you're looking for a good inspiration moment during your build season, just go to their blogs and you can find you can see what they're prototyping with currently. So you can see here they decided to go with an arm. They decided to go with an arm instead of an elevator, and their intake had to be their intake was angled while picking up cubes. So they decided to they had to build their intake like that and make sure it had enough power to pick up a cube at that angle. Another thing you can see that's a good thing that they did is that they used wood frame. They used a wooden frame to simulate robot movements, but I wouldn't recommend using Omni wheels. I just recommend using because that's just like a longer waste of time instead of just using a robot card, but Omni wheels are still fine in this case. So 254. So you can see here they have an intake prototype, and if you guys are here for 2018 season, you might be thinking to yourself, this is not the intake that I saw in the robot. So what they did is that they decided that their elevator, their arm, and their drivetrain were more important than their intake, and they actually started prototyping their intake in week 5. And they're like, you know what? We're just not going to make an intake. We're just going to copy it from the best team that there is. And that's what they ended up doing. They copied from 1323 and had a really good intake. So here you can see how sketches are important. So this is a classic example of drivetrain. This CAD actually hasn't changed that much throughout the years. And the way that I know that is if you Google 254, they publish technical binders every year of their drivetrain and all that kind of stuff. So you can see what has changed and you can take inspiration from their designs. So when I was talking about sketch constraining earlier, now you can see how they're able to simulate a cube here, and a cube here. So what the purpose of that mechanism was is that they were trying to flip a cube into their elevator and then shoot through the elevator. So that by simply just designing that in CAD, they're able to get rough measurements and estimates of the different ways that they can, the correct measurements for how they can do it in real life. So you can see here, these are the more final stages of CAD, and you want to do it. You want to do a 2D sketch first, because anyone that CAD knows here that if you figure out that one hole is wrong and you're like this far in, it's a pain to change it down to the long end, since changing that one hole might affect a bunch of your other constraints. So you want to look at it in the 2D perspective before you go into a 3D perspective. So this gearbox on the left might be really complicated to look at first, but the main function of this gearbox is to switch between gears, and for most cars, we know that we have to switch between gears to go faster from high gear to low gear, and high gear has higher acceleration. So basically, they had one gear that they used to accelerate their elevator to its fastest speed, and they switched to low gear when they didn't have to use that much. Okay, so here we can see the final results of what it looked like. So that intake doesn't look like anything they had on their robot before, but so they made a design call where they didn't have to prototype the intake as much. Okay, we're almost at the end, but here we go. So here we see 971. This is another team that CADs everything before they build everything. But like I said before, we shouldn't prototype drivetrains, but that wasn't exactly the case for 2016. Does anyone remember what the 2016 game was? Stronghold. It was a very rough terrain, right? So there was a lot of rough terrain, and there was a lot of obstacles you had to face. So many teams prototyped their drivetrain because they needed to find the optimal placements for their wheels so that they can combat the rough terrains more effectively. Okay, so let me just talk, I'll talk about the intake later, but you can see here how they started off with 80-20 prototyping and they ended up with this complicated shooter. Keep in mind that if that is the mechanism that works for you, you should keep it. You don't have to make it look like this. They just did that because for them, they didn't have the space to keep that on their robot, or that's how they chose to build it. If this works for you and you have enough space to put it on your robot, there's nothing wrong with 80-20. You can still use it like that. Here's the final design of the robot. You can see that they changed their prototype mechanism from rollers to eventually they use mechanism wheels and omni wheel. How that works is that mechanism wheels, they're positioned, they have rollers on the side that are at a 45-degree angle, so the ball moves towards the center and the omni wheel just pulls the ball into the intake. This passive roller mechanism didn't work as well, so that's why they switched to mechanism wheels. So keep in mind that actually switching between wheels can also make a big difference. So you can see, this is our team, this is how we prototype. You can see how there's a similarity between all of these prototypes, and actually our 2018 intake was very similar to this. And what we thought was, since the GameCube is around the same size, we thought it would work fine, and it ended up working fine for us. So that's how we approached this.
Intake. Very nice.
Enough of that. So here's a few more examples of prototypes. So here, if you guys know what 1678 is, you might see a similarity between that team's intake and ours. One of our mottos is copy from the best and invent the rest. So we just looked at 1678's competition like week 1 or week 2 or week 3, and then we're like, that's a really good cargo intake. Let's see if we can improve ours by building one. So we did that, and it did end up being as effective for us. So we didn't go with that design in the end.
Love it.
So yeah, that's another hatch intake that worked really well for us, but didn't work out in the end since our intake opened and didn't have to stay like that. So when you're trying to get ideas for prototyping after build season, you just gotta remember that FRC isn't only restricted to NC. You should watch other regional competitions like West Coast and Palmetto, since they're very competitive. They might have designs that you didn't think of before. So West Coast usually includes San Francisco and Silicon Valley. It's really good to watch in 971, 254, all sorts of amazing teams compete there, and you can look at their designs and be like, oh, I can do that. So here are some prototyping resources that you can look at during build season. Spectrum 38 to 47's blog, you do the website. RI3D, which is basically a group of people, what they've decided to do is that they, it's like FRC students that are no longer in FRC, so they look at the game like, okay, let's build a robot in 3 days and see what happens. And they document the whole thing and they release a reveal video at the end of the process. So that's one way you can, that's one way to get an inspiration as well. And Triple Helix does the same thing. They have a YouTube channel. You can just look it up and they post their prototypes during build season. Here's some prototyping resources for off-season. So prototyping during off-season probably includes, which is now, you can test designs that your team hasn't done before. So if you're thinking about maybe switching to swerve drivetrain, you don't want to prototype that during the build season. You might want to look at that during off-season instead. And ways you can find inspiration for such mechanisms are looking at 254's technical binders, which are very detailed. They have a lot of good pictures of their robots so that you can look at how exactly they're built. And then CAD models of other teams. We publish our CAD on GraphCAD, and so do all of these other teams. So you can look at their CAD models and take inspiration from them. And lastly, you gotta remember, the build season never ends, and that's actually true for this season because there is no end for build season. But even after competitions start, the build season doesn't end because for us, we started with that intake during competition season, and then we thought that the hatch intake wasn't as effective, so I think a week before states, we were able to prototype that mechanism and come up with something much more efficient. So you always gotta remember that even after build season ends, even after competition season starts, you should always keep on prototyping until the end until worlds or states. So key points for this presentation. You want to always use quick concepts for your initial design. You don't want to limit yourself to one design. You have to give unconventional designs a chance, and you got to remember when to skip prototyping. And that's about it. Any questions? Okay. That's about it.
Oh, wait, quick question.
Oh, yeah.
Where did you say you update your CAD files to?
GraphCAD. So it's like a group CAD file. It's like a community service website where like people upload CAD models all over all teams. If you search up like 2019 hatch intake, you probably get something. Or if you go to our website and go to resources, there's a link to our CAD file on there, so you can for 2019. Any other questions? Yes.
I've seen where you can put CAD on Blue Alliance too. Do a lot of teams do that?
No, but so you saw how 148 and 118, they don't put it on Blue Alliance, but what they do is if you search up 148 CAD on Google, their website will pop up, and you can just, on their own website, they have the CAD models there, or on 118's website, they have the CAD models there. Similar, and there's an FRC Discord server. If you join that, there's a channel in there which is specifically dedicated for CAD files. You can find, there's links to like not hundreds, like tens of hundreds of CAD files in there, so you can use that as a resource during off-season. Any other questions? Okay, I guess that's the end of our presentation.